Hello guys, we're going to look at section 4.5, which is what we call LHopitals Rule. So LHopitals Rule is very useful when I want to determine the asymptotic behavior. So what's happening as we take a limit as it approaches infinity. And why is this important? Because we've been looking at how do we graph a function. So what's happening at the ends of our function? What happens if I have an asymptote? Okay? And so we want to consider this function here, the limit as x approaches a of f of x over g of x. So LHopitals Rule says that if when I take this limit, I get the indeterminate form 0 over 0 or infinity over infinity, then I can rewrite this limit by using its derivatives. Okay? And so we say by using its derivatives, if I write the limit as x approaches a of f of x over g of x, we can rewrite this as the limit as x approaches a as the derivative of the original function over the derivative of the denominator, the numerator and the denominator. Okay. Keep in mind, this is not taking the quotient rule because it's a quotient. This is just saying you're going to take the derivative of the numerator and the derivative of the denominator, and the limit of this new function will give you the same limit. So formally, LHopitals Rule says if we have an f of x and g of x that are both differentiable, okay, and the function evaluated at some a and the numerator and the denominator both equal 0, that means I get 0 over 0, then I can rewrite it by taking the derivative of the numerator and the derivative of the denominator. Keep in mind, we don't want that denominator equal to 0. Okay? And then the second part says it also exists if I get plus or minus infinity over plus or minus infinity. Okay? So the rules will still hold, okay, but only for these indeterminate forms. So let's look at an example. If we want to take the limit as x approaches 2 of the function x cubed minus 8 over x to the 4th plus 2x minus 20. Okay? If I plug in my 2's, it's always our first course of action with any limit, we get 0 over 0, which is an indeterminate form. So LHopitals Rule, I'm going to put a LH, it says we're doing LHopitals Rule, okay, says that I can rewrite this limit as the limit as x approaches 2, and now I'm going to take the derivative of the numerator, which would be 3x squared, over the derivative of the denominator, which is 4x cubed plus 2. And so now if I take this limit, that means I can, of course, first course of action is to plug in again. Okay. And I get 12 over 34, which simplifies to 6 over 17. So this says that my original limit as x approaches 2 of x cubed minus 8 over x to the 4th plus 2x minus 20 is equal to 6 over 17. And here again is the worked out solution that we've already done independently. Let's look at another example. If we want to take the limit as x approaches pi over 2 of cosine squared over 1 minus sine x. In doing this, we see cosine of pi over 2 is 0, so that 0 squared is 0, over 1 minus sine of pi over 2 is 1, so we get 0 over 0. So LHopitals Rule applies. Okay? And so when we take the derivative of, this is our L'Hopital applying, the derivative of cosine squared, remember this is cosine x to be squared, so its derivative, we would use 2 times the derivative of the inside, not derivative, 2 times cosine to the first power times now the derivative of the inside, which would be a negative sine x, okay? And then the derivative of the denominator, of course, 1 minus sine x, the 1 is 0, and the derivative of sine is cosine, so I have a negative. And what happens here is our negatives cancel, our cosines cancel, so we're just left with the limit of 2 sine x. And then the sine of pi over 2 is 1. So we get 2 times 1. So this limit is equal to 2. Let's look at this example here. This is the limit as x approaches 0 of x times the natural log of x. So if we recall, what is the natural log of x? It looks like this. Okay, and let's say we want to do the limit as x approaches 0 from the right, because we know that the natural log function isn't defined for values, only defined when x is greater than 0. Okay, so if we come from the right, we see it goes to negative infinity. Okay, so we have 0 times negative infinity. And 0 times negative infinity is not one of our forms. We have to have 0 over 0 or infinity over infinity. So what we're going to do is we're going to rewrite this expression. So if we write it as the natural log of x over x, right, in this form, we'll get negative infinity, and then in this form, we got to make that be to the negative 1 if we bring it to the denominator. Okay, and so of course x to the negative 1 is 1 over x, and if we look at 1 over x, okay, as we approach from the right, it goes to positive infinity. Okay, so again, we're only looking at 0 from the right, so that's here. Okay, so now I have it in the form of L'Hopital's rule. I have an infinity over infinity. So L'Hopital would tell us that we would take the derivative of the numerator, and of course we remember the derivative of the natural log of x is 1 over x, and the derivative of x to the negative 1 would be negative x to the negative 2. Okay? We'll need to do a little algebra, and we'll have 1 over x times, I can rewrite that as negative x squared, and so because I just brought this as a negative 2 here, okay, and I can bring that to the numerator, it becomes positive. So one of my x's cancel, and I just have the limit as x approaches 0, from the right of, now I just have a negative x left. And when I plug that in, I get 0. So our original limit that we were looking for is going to be equal to 0. Again, we've worked this out, but this is the problem that we've just worked. So these are anything in the form of 0 times infinity. Please excuse me. 0 times infinity. That's plus or minus infinity. Sometimes when we're applying L'Hopital's rule, we might have to apply it twice or 3 times or as many times as needed until I don't have one of my indeterminate forms. So if we want to take this limit here, the limit is x approaches 0 of e to the x minus 1 over cosine x minus 1. If we plug in a 0, we get e to the 0, of course, is 1, and then 1 minus 0 minus 1, we get 0 in the numerator. And then cosine of 0, of course, is 1, and 1 minus 1 is 0 again, so I have to apply L'Hopital's rule. So this is my step for applying L'Hopital's rule. So, of course, the derivative of e to the x is e to the x, the derivative of negative x is negative 1, and the derivative of 1 is 0. In the denominator, the derivative of cosine is negative x squared, negative sine x, and the derivative of 1 is 0. Okay? But when I plug in e to the 0, I get 1 minus 1, and then, of course, sine of 0, a negative 0. So I have 0 over 0 again. So now I have to apply L'Hopital a second time. So the derivative of e to the x is e to the x, and the derivative of 1 is 0, so it's not there. The derivative of sine is cosine, and I'm going to keep my negative. So now when I plug in my e to the x, I'm doing my e to the 0, I get 1. And then, of course, let me write this as the limit as x approaches 0, of negative cosine of 0, I get a negative 1. And so now this limit, we see applying L'Hopital's rule twice gives me a negative 1. So now keep in mind, when you're using L'Hopital's rule, it just can't be applied to any function. It has to be applied to one that has an indeterminate form of 0 over 0, infinity over infinity. Let's see what happens. If I take this limit here as x approaches 1, I can just plug 1 in. I get 1 squared, 1 plus 1 is 2, and then 2 times 1 plus 1 is 3, so I get 2/3. So we know from what we've been doing since day 1 that the limit is 2/3. Let's see what would have happened had we applied L'Hopital's rule. L'Hopital's rule says I would take the derivative of the numerator and the denominator, which would give me 2x over 2. The 2's would cancel, and I take the limit of 1. Okay, limit of x as x approaches 0. Is that right? Looks like it should be, oh yes, this should say 1 here, guys. Sorry about that. So if I take the limit as we approach 1, we get 1. And so using L'Hopital's rule, I got 1, but the actual limit of this function is 2/3. So we see L'Hopital's rule cannot be applied in just any limit, only the cases where I have these particular indeterminate forms. Let's look at this limit here. The limit as x approaches 0 of 1 over sine x minus 1 over x. If I plug in the 0, I actually get something in the form of infinity minus infinity. Now keep in mind, when I have infinity minus infinity, this is not one of my rules to use L'Hopital, not one of my forms to use L'Hopital. It is indeterminate, but it is of this form here. So we need to rewrite this. And how do I rewrite it? I get a common denominator. And so a common denominator of x and sine x is going to be x sine x. So I need to multiply this part by x and this part by sine x over sine x. And we get this new term here. Now, if I take the limit of this new term, I get 0 over 0. So by rewriting it, I actually have an indeterminate form that I can use L'Hopital. Okay, so this step is just our rewrite. Okay, and here, let's use L'Hopital to take the derivative. So the derivative of x is 1. The derivative of sine x is cosine x. And in the denominator, I need to use the product rule, x times x. So I take in this case, they did it upward, but it's okay. They took sine times the derivative of x is 1, plus the x times the derivative of sine is cosine. Okay. If I plug in my 0, I actually get 0 over 0 again. Okay? And so I now have to apply L'Hopital's rules a second time. Okay? And so taking this derivative, we'll get sine x over here. It'll get sine x, and we have to use the product rule again and combine like terms. We'll get 2 cosine x minus x sine x. Okay? Plugging in my 0, in the numerator, sine of 0 gives me 0. And then 2 times cosine of 0 is 1, minus 0 times sine of 0 is 0. So I get 0 over 2, which is indeed still equal to 0, and which is okay. We can have a 0 in the numerator, but not in the denominator. And so now we've applied L'Hopital's rule twice, and we've gotten our limit. So the first few problems we were looking at, we were taking the limit as we approach some a. Okay? But what happens if we want to know what's happening at the end of this function? So what would we do if we want to take the limit as x approaches infinity? Okay? So L'Hopital's rule for limits at infinity is going to be similar. Okay? So as long as I get one of my indeterminate forms, 0 over 0 or infinity over infinity, I can rewrite my limit as the limit of the derivative of the numerator divided by the derivative of the denominator. Okay, and this will hold for plus or minus infinity. Okay, as well as, of course, yes, plus or minus infinity, as well as that's it, one-sided limits. We can do one-sided limits too. So let's look at this example here. We want to take the limit as x approaches infinity. So we want to take the limit as x approaches infinity of x times the natural log of x over x squared. Okay, so x times the natural log of x happens to be this function q of x here. We see that it goes off to infinity. And so over x squared, we of course know x squared goes off to infinity. So now L'Hopital's rule holds. Okay? So before we do that, okay, anytime we're doing a problem, we want to simplify as possible. So I have an x in the numerator and 2 in the denominator, so that changes to the natural log of x over x. Okay? Likewise, I'm still going to get infinity over infinity because the natural log of x looks like this. It goes to infinity. And of course, the line x goes to infinity. So now this step here, I can apply L'Hopital. In applying L'Hopital, of course, the derivative of 1 over x, natural log of x is 1 over x. The derivative of x is 1. And so if we recall, the limit of 1 over x is just 0 as we approach infinity. And so we also know what that function looks like. We see as it gets closer to infinity, it's getting closer and closer to 0. And so therefore, we get this limit by taking the limit at infinity. L'Hopital still will hold.